Okay, so we will talk about computational geometry. It is basically the need area for its developed algorithm for solving the geometric problem. So, first of all, what are the simple basic geometric object? A point, it could be in any dimension, here it is in 2D, but it could be have any dimension. A line segment, or a line. So, these are the basic geometric object. Now, based on this, suppose we have some basic structure, basic geometric structure. Basically, suppose we have some points. We have some points. Now, the problem maybe is to finding the polygon. So, basically, we need to so this is the polygon. This is the closed loop which will not intersect with each other. Then the next problem could be triangulation. We have some points and we have to find the triangles. So, this is called triangulation. And the second problem could be convex hull. We have some point and we have to, so this is the convex hull. So, we have to close these points with such a region that if you take any 2 points, it should be inside in that region. So, these are the problem which are used in fluid mechanics or any other area. So, now today we will talk about what is called orthogonal range search problem. So, we will talk about orthogonal range search. Okay. Now, basically the problem is, suppose we have some points in any dimension. This could be a database problem. This is, say, we are in 2D and we could be in 3D also. Suppose these are the points in the space. These are the 3D points. Okay. Now, we have given a orthogonal range. For 2D, it is a rectangle. So, we have given a rectangle and we have to find out the whether is there any point in this rectangle or not, and how many are they. So, these are the query. Is there any points in this rectangle? This is one query. How many are they? We have to output all the points who are in the rectangle. So, this is the query. In 3D, this is a box like this. So, 3D box. Okay. So, this is orthogonal, means this is parallel to the axis. Now, this could be a database problem. So, it could be d-dimensional. So, like say we have a student record. So, each student is having say many attributes like many fields, like the marks in the algorithm course, marks in the mathematics, marks in the computer science, overall marks. So, these are the attributes. So, these are the field. So, how many subject we have different dimension. Now, suppose a company came and they are asking for some specific marks they are asking. So, they need the mathematics marks to be lies between 70% to 90% maths mark, and they want the edge should be like this. So, they can fix a box in this over this database, and they can try to get this query. So, this is one applications. So, now how to solve this problem, this orthogonal range search query. So, one shot what we can do, suppose we are in 2D. So, we know this coordinate. So, this is say x1 y1, this is say x2 y1, and this is say this is x1 y2, this is x2 y2. Suppose we have given this rectangle. Now, how we can do this? We can just take all the points and we can verify their x coordinate, y coordinate. If this is belongs to this, then we are done. So, if what is the time? So, that is the Naïve approach, or that is the one shot approach. So, what is the time complexity for that? We have to do it for all the points, and if it is n dimension, a d dimension, this is typically n into d. But if d is a constant, I mean, then this is order of n. But we want to do something better than order of n. So, what we can do? Can we use some sorting algorithm for this? Suppose we are doing this for 1D. So, 1D orthogonal range search. Okay. So, 1D means we have this line and there are some points, lies in the points. Okay. And we have a query range, and we want to report all the points lies between this range. So, that is the 1D range search. So, how we can use sorting? So, we can sort the points and then we can do the binary search based on these 2 points, and whoever in the middle we can report them. So, we can do the binary search on based on these 2 endpoints. 2 endpoints. Okay. So, how much time it will take? It will take basically, so sorting will take n log n time, because if it is static, then it will take, we have, but that can be added in the p processing step. So, online step, it is basically the binary search, it is basically log n plus k if we have to report all the points. Okay, but this we cannot extend for higher dimension, because we have to sort which coordinate. Higher dimension we have many coordinate, x coordinate, y coordinate. So, we cannot extend this idea for higher dimension so easily. So, another way is to use the interval tree. We know the interval tree. So, what we can do? We represent a point by the interval of length 0. Okay. So, we replace all the points by interval, and then we form the interval tree, and then we have a query interval which is given, and then we search, and then we once we got a point, we delete it from that interval tree, and we will again make it as a new interval tree. So, this way. So, this will take the time basically order of k log n. Okay. So, now we are going to discuss a method which is called range search tree, which will give us order of log n plus k, and that is easily that method can be extended for 2D also. So, this is called 1D range tree. Range search tree or range tree. So, the idea is to keep all the elements in the leaf, and we will form the BST, balanced binary search tree. So, let us take an example. Suppose these are the numbers we have, these are the elements we have 12, 14, we have 17. These are the elements. So, we want to put everything in the leaves. So, leaves contain the inputs. So, 41, 42, and then we have here 43, 59, 61. So, these are the input. Now, we want to put this input in a leaf level and we want to form the BST. So, what we do? We can do like this. We can do like this, and here also like this, like this, like this, like this, like this. Then in the top the root is okay. So, this we want a BST. So, BST means if we take a node, all the key value in the left subtree is less than x, all the key value in the right subtree is less than x, greater than x, and this is the key value of the root of that node. Okay. So, now, so what are the values we can put here? We can put here any values between 1 and 6. Okay. So, but we want to put the minimum of the left, maximum of the left subtree. So, this will put 6, this will put 1, so this will put 12, and this will put 14, this will put 8, maximum over the left subtree. Like this we fill this 26, 41, then 35, then this is basically 59, 43, then this is 42, and this is 17. So, this is called 1D range tree. So, this is basically a BST, we can make it a balanced binary search tree. Okay. So, now suppose we have given this. So, now how we can put a query? Suppose we want to query say 741. This is our query, and we want to get all the elements in this range. This is 1D range search. So, this is the one dimensional orthogonal range. So, that means this will be basically from here to 41. So, here to here. Okay. So, that means all the elements from here to here. So, if we can report these all the all the nodes like this, yeah. So, basically instead of reporting this node individual, if we can report all the subtree, these are the subtree whose leaves are basically our answer, leaves are basically our outputs. So, if we can output these subtrees, then we are done. Then we can go to the corresponding leaves and we can output those leaves. So, that is the idea. So, we will just try to report this subtree. If we just report 8, that means a subtree rooted at 8. If we just report 14, subtree rooted at 14. So, tree rooted at 14. So, that means all the leaves of that will be the output. So, like this. So, this is the idea of 1D range query. So, let us just draw what we are doing. So, basically the 1D range query. So, we want to get those subtrees. So, what we are doing? We are starting with the root. So, this is the root. Okay. And then we may see nothing is relevant in the right part of the tree. because nobody is there in the right part of the tree. So, then we will go to the left part of the tree, and here if we realize that nothing is relevant in the left part of the tree. So, we will go to the right part again. So, this way we continue, and at some point of time we will reach to a node where we realize something is relevant in the left part and something is relevant in the right part. So, this is called split node. So, split node means it is a node where something is relevant in the right part, something is relevant in the left part, something is relevant in the left part, something is relevant in the right part. So, in the split node what we do? Then we continue traversing. So, we traverse this. So, maybe we realize that everything here is our in the range, then we go to the right like this, then we realize everything here is the relevant, then we do it for the left part, and then we see everything here is relevant, we go to the right, then like this. So, these are the, we report all these subtrees, we report the root of these subtrees, and that will give us the basically nodes. Leaves are basically the nodes which are in that range. Okay. So, this is the general description of the range thing. So, now how to so let us write the pseudocode for this. Then it will be more clear. Okay, so, this is basically 1D range query. So, we have given the range tree, 1D range tree, and we have the orthogonal this x1 interval x1 x2. So, what we do? We first take the root, and then we continue until we reach to a split node. So, how to do that? So, while w is not nil, not a leaf, if it is a leaf we stop and we check whether this node is belongs to that interval or not, and this is and x2 is less than key value of w, or this is or key value of w is less than x1. So, that means we will go either left part or we will go to the right part until we reach to a split node. Now, do if, so this is under while, do if, so if x2 is less than key of w, that means we have to go to the left part, then w is the left of w, otherwise else w is the right of w. So, this will stop either w is a leaf node or w is a split node. So, that means we will go either left part if everything is this side or this side, you will go to the right if everything is that side. So, this will continue until we reach to a node which is basically that split node. So, we check this is the root like this until we reach to a node where something is relevant over here, something is relevant over here. So, that is the split node. So, we reach to a split node, otherwise it is leaf. If it is leaf, we check their value, then we if it is in that range. So, that we have to write. So, so this is if w is a leaf, w is a leaf, then we output w. If the key value of w is lies between this range. Okay. Otherwise, w is a split node. Then we have to get the points, we have to go to the left part and also we have to go to the right part. So, first we will check for the left traversal, and the right traversal will be the similar. So, let us try to write the left traversal. Okay. So, this is the basically, so W is not a leaf node. So, we are going to the left part. So, this is basically left part of W. So, now what we are doing, if V is not a leaf, then we check do if x1 is less than equal to key of V. That means, so this is the split node which is V. Now, this is basically now we check whether anything is interesting in the left part of V or not. If anything is interesting in left part of V, then we will output the right subtree rooted at this. So, that is the check. If x1 is less than this, then that means we have to go further left part, that means everything is relevant over here in the right part. So, this is basically V is basically this one, this is the split node, V is basically this one. So, if everything, if we have to go to the left part, then the everything is right part is the relevant. So, then output subtree rooted at right of V. Okay. And we then go to the left of V again, else we go to the right of V, else means if this is not correct, and this we continue until it is a leaf node. Once it is leaf node, then we check whether that that node belongs to the this in the range of that. So, this is the pseudo code for finding the points in that range. So, let us analyze this. Okay. So, how much time we are spending here? So, suppose there are we have to report. So, it is basically balanced tree. So, it is basically log n time. So, sorry, log n time required to find the log n subtree. There are maximum log n subtrees. So, how many subtrees are possible? Log k actually. So, this is log n we can write. So, log n subtree can be reported and in the log n time, and then once we report the subtree, we have to print all the outputs. So, that will take time log n plus k. Okay. So, this will be the to print the leaves of each of this subtree. Okay. Now, how much time it will take to for that query, that how many nodes are there. So, this query can be tackled by augmenting this data structure. We can store in each node, we can store the size of the leaves. So, that way we can augment this and we can have the query in log n time. Okay. So, now how we can extend this idea for 2-dimensional range search. We have seen the 1D range query where the points are on the one dimension. Now, if the points are from 2D points. So, we have some points and we have given a range which is basically a rectangle. This is the range, and how we can extend this 1D to 2D. So, what we do? We first make a primary tree based on the x coordinate on the points, and so we will just make a primary we called it primary tree, primary 1D range tree on the points based on the x coordinate. Okay, so points are basically 2D. So, we will make a primary range tree based on the x coordinate, that is the primary 1D range tree, and then for in that tree for each of the points, suppose we in that tree this is a point, we have another range tree which is called secondary range tree, that is also 1D range tree based on the y coordinate on the points where these points are the leaf rooted at this node. So, for each of this node in a primary range tree, we will have a pointer to a node of the secondary range tree, where with the secondary 1D range tree is made by the y coordinate. So, that is the idea. So, first if we search in this primary range tree, so we will get all the points lies between this strip, this is x 1, this is x 2. Now, this is basically if we do the range search, we are going like this, then suppose this is the split node. So, we have something interesting here, something interesting here. So, from here suppose this we all print this node, then we go this side, then go here, suppose we all so go this side here. Suppose these are the tree we are getting in the primary range search, then from this side also we are going this side. So, this is okay. So, like this. So, these are the basically tree we are outputting after the primary range search. Now, we have a secondary range tree which is made by taking all the points of from the primary range tree. For this point we take all the points over here and we make a secondary range tree based on the x y coordinate. So, this is pointing to a so we have similar tree will be similar size. Okay, so these are the trees. So, okay, so these are the we have similar type of range tree based on the y coordinate. So, now we have a pointer from here to here which is pointing to that now to that tree. Now, we will do a search in this tree. So, in this tree all the points are satisfying the x range. Now, we have to search who are the points also satisfying the y range. So, this is basically we do the again the range search in this based on this. So, we got a split node, then we go left right like this. So, like this we go here like this. So, these are the points is also in the y coordinate, and so this will output. So, this is the extension of the 1D range tree. So, in this 2D range search tree we have a we have a secondary range tree based on the y coordinate on all the points. We take the subtree rooted at this point and we make another range tree based on the y values. So, this is the idea. So, now what is the time complexity for this? So, we are doing twice this. So, this is basically log n raised to square. Now, if we are to report k points, if there are k points, then the time will be basically k plus log n base 2 square. Okay. And what is the space? Space is basically order of n log n, because there are log n such tree, and for each of these element we are having a secondary range tree, and the height of that is log n. So, it is n log n the space, and the p-processing time is to make this is also p-processing time is basically also order of n log n. Okay. Now, we can extend this idea further for more than 2 dimensional. So, if it is 3 dimensional, then we will have another range tree 1D based on the third coordinate z axis, z coordinate like this. So, if you just extend it for the d dimensional space, then our query time will be, this is in general will be k plus log n base 2 to the power d if we are in d dimensional points like database, and this will be in log of log n to the power d minus 1, and the p-processing is p-processing time is order of log n d minus 1. Okay. So, this is the case where it is the general form of d dimensional time and space and p-processing. Thank you.